All right, my name is Shawn Edwards. If you were just here, I was in the previous talk. So I am a cyber adversarial engineer, which just means hacker at the MITRE Corporation. Hacker, I like to hack things, make things, and learn things, which is fun to me. So just a little bit about MITRE, give it a little bit of sales pitch, of course. We kind of made the phrase up, but we do adversary emulation. It's basically red teaming, but rather than general red teaming of using whatever works, you use the TTPs, the tactics, techniques, and procedures of specific threat actors. So we take the open source knowledge of like APT3, APT29, and use what they do in the real world to emulate their behavior and operations, which just ensures that the techniques that we use are accurate to what's done in the real world. We're pretty well known for the attack framework, which is a public wiki of attacker techniques. And Caldera is also a thing that I really like, which is a modular framework for automating remote access tools and adversary emulation. And I'm going to skip through that anyway. All right, so today my talk is about in-memory malware and specifically doing it with .NET. Now, a lot of people think that all-in-memory malware is a new, really advanced type of malware, but it's actually not. Process injection, which is just taking code and taking additional code and running it in your process or another process, has actually been around for a really long time. It's just that people are doing it a lot more these days because they have no other choice. So while previously you could drop stuff to disk and run your malware that way, these days you just can't get away with that in most environments. So everybody's trying to figure out how can we take our tools and run them from memory instead. This has been made a lot easier by both open source and commercial red team tools, as well as a few leaks, and I'll leave it at that. For this talk, we're only going to be discussing in-memory malware in Windows. I'm not really a process injection guru on Linux. You can do a lot of this stuff in Linux too, just not with .NET as much. So another phrase for running code from memory is reflective injection. If you've ever seen that alert, that's probably what it's going to show up as, which reflection is a fancy phrase for using code that's loaded from memory rather than from disk. And injection is just getting it to actually run. So there are historically a few main ways of doing this. Shellcode is the one that most people, well, it's the most prevalent. All shellcode is machine code. So it's usually handwritten in either assembly or C, and you take whatever the machine code is that can run directly on the processor, and you use that as a payload or as a way to download and execute another payload. Reflective DLLs, it's just a DLL that can be injected into a process, which makes it easier because you don't have to write shellcode, you can just write a DLL. And the same way with EXEs using PE loading. PE is the format for Windows executables as a file format. And there are a lot of other ways to do it, but those are the main ones in Windows. There we go. Okay. So these are just a few of the Windows API calls that are used to inject shellcode. There are a lot more of them, but these are the main ones. So most people, if you've done any shellcode injection, you know create remote thread. That's literally a built-in Windows API call that just creates a thread in a different process. Underneath the hood, it actually uses some other ones. So if you want to avoid that one, you just use the ones that it uses, and a lot of stuff won't detect that, and that would be NT create thread. And a bunch of other semi-advanced ones that people have developed as AV and EDR gets better at detecting basic injection techniques. PE files, there are a number of ways to take EXEs and DLLs and run them from memory. There's just reflective DLL injection, reflective PE injection, and then what have been heard about a lot recently is process hollowing and process doppelganging. I won't go into details on those, but if you want to look this sort of stuff up, that's what you can Google. Now, modern Windows Tradecraft, though, has shifted to using the .NET framework underneath the hood. And there are a number of ways this shows up. The main one is through PowerShell. So a lot of malware these days is in PowerShell, or it was in PowerShell. The other advantage of it is that you can load code easily from memory. And we're going to go through all this stuff in probably more detail than you want. So what is .NET to begin with? So .NET is, if you're familiar with C# or PowerShell, .NET is a framework on which all of those languages operate. So it was made to rival Java. And if you're familiar with Java, it runs through a runtime environment. Just like Java, .NET has a runtime environment called the CLR, the Common Language Runtime. It has an intermediate language, which is actually an object-oriented assembly language that gets compiled just in time for execution when you're running C# or any other .NET language. And all of the languages follow a common spec, which is why they can be interoperable with each other, and you can use one language from another. I'm pressing the wrong key. There we go. So it was developed because Microsoft wanted to have a good application framework for developing client-server models that was not Java, mainly for competition issues. They had their own in-house version of Java actually for a while, but they wanted to create one that was not reliant on a particular language, but that could actually build languages off of over time. And because of that, it's now integrated into the Windows operating system at a very deep level. So how does .NET actually work? So regardless of the language, your source code gets converted to CIL, the intermediate language. That is referred to as managed code. Actually, any code that has to run through an interpreter is also referred to as managed code, but in .NET specifically, that would be CIL. The main thing of interest with this is that CIL is also, or managed code is also interoperable with native code. So native code is the term for code does not have to go through a runtime environment. So languages like C, C++, they would be native, whereas C#, Java, they would be managed. And some languages you may be familiar with: C#, F#, PowerShell, JScript, IronPython. Because all of these are .NET, they all work with each other. So you can use code written from one of them in another one. But how does it actually run? So when you write a C# program and it gets compiled, you see an exe or a DLL. But what is that actually? So it's a .NET assembly. And the .NET assembly file format is an extension of the PE format. The .NET assembly, though, contains managed code rather than native code, and it has another crucial difference, which is that the metadata about the code is included along with the code. And a .NET assembly was designed to be the boundary for all security, code referencing, and version control, everything. So when you use a .NET library, you're loading a .NET assembly. Each assembly runs inside of an application domain, and it's basically just a box for assemblies to run in. Each application domain can contain multiple assemblies, and multiple domains can exist in the same process. The theory behind this is that you could isolate each app domain in the same way as you would a process. So theoretically, you're sort of having multiple .NET processes inside of one Windows process. This gets weird, though, because Windows threads can actually move between application domains. So now your analogy breaks there. Wrong button again. All right. So it can also run as scripting languages. Because they all use the same spec, it's relatively really easy to create a scripting language off of .NET. You don't have to write your own compiler other than to CIL. You don't have to get it to run on the native hardware. You just get it to compile to one intermediate language, and magic happens, and it becomes interoperable with everything else. So why is it currently popular? .NET Framework, as I mentioned, is heavily integrated into the operating system itself. Windows has put a lot of investment into the .NET Framework, so all of their additional features and tools are written in .NET. For example, all of the Windows Store apps are written in .NET. The other the one that's useful for red teamers and malware authors, though, is that it allows all-in-memory operations because there are whole APIs built for loading code from memory. If you're familiar with using .NET tools for offensive use, you're probably familiar with it through the Cobalt Strike command execute assembly, which lets you take any arbitrary .NET assembly and run it as if you were running it from the command line off of disk, but you're running it from memory instead. It provides the same user experience. So seatbelt is an example of a host enumeration tool that shows you, all the details you might want to know, like what AV is running on the system and stuff. That's all you have to do to run it from memory. You don't have to drop it to disk, nothing. But .NET Tradecraft is not actually new. It's just popular now. C# rats have been around for a long time. Quasar rat and a bunch of others. The difference is that previously the C# rats were doing the same thing as the rats in C and C++, whereas now people are not just exploiting with .NET, they're exploiting .NET itself. As PowerShell became heavily monitored by defenders through AMZ and script block logging, attackers had to figure out a way, how do we transfer our tradecraft while still being able to run from memory? And C# was the way to do it, because all the underlying APIs are the same, you just can't run it through PowerShell.exe. So the main pro, again, is that you can load code from memory. Those 2 lines of code are at the bottom are just about all it takes to take a .NET assembly and load it and run it. Now, the downside of that is that you can only do it from C# or .NET language. But the .NET framework supports loading and execute managed code from memory. You can dynamically generate code on the fly and then execute it, and then also do reflection on it, so you can be like, okay, the thing that I just made dynamically, what are all of the properties and the types and everything in it? It gets insane. And it also supports delegation, which is basically function pointers, which you can do some really weird stuff. If you've heard of, in air quotes, fileless execution vectors, usually what they are is some .NET scripting language underneath the hood. Some APTs have had 0 days for certain web browsers, like Internet Explorer and Edge, and usually what they're doing is getting .NET code to execute outside of the sandbox. So PowerShell, VBScript, and JScript are all .NET scripting languages. JScript is the one that's especially leveraged for this stuff. It's a Microsoft implementation of JavaScript that is used behind the scenes for their web browsers. The other benefit of using .NET is that it's interoperable with all of the other frameworks that Windows uses, like COM, for example. So you can use COM, you can use OLE, you can also use Windows Communication Framework, which is a way to pass objects over the network in a serialized form. So you don't have to just pass data, you create an object, send it down to your target, and it has the whole object in memory, not just the data of the object. You can use pinvoke to use existing Windows DLLs. So all of the underlying Windows API you can take advantage of. It also has extensive .NET specific APIs. And you can even, if you want to, export functions to be used by C and C++. It also lets you write unsafe code, which is basically just, C-style pointers and C#. I'm going to skip through some of this stuff. So the downside of it, though, is that .NET assemblies, because the metadata is associated and stored with the code, you can take your .NET assembly and just reverse it to source code, including even getting comments and stuff. The other downside of it is that you can't inject it directly into a different process. So you can, if you are using C#, load a .NET assembly, but you can't say, hey, Notepad or Explorer, whatever other process you want to inject into, you can't do that directly like you can with C or C++. And .NET does provide a lot of tracing utilities that lets you monitor what's happening in the runtime. The main one is Windows Event Tracing, which can be used to actually pull out the intermediate language, the assembly language, and function signatures from memory as code is executing. All right. So mostly attackers are using C# to do this, just because it's an easy language to use. And the end product is either an EXE or a DLL. So who started using it for red teaming? Well, we don't know entirely who, but publicly who would be Nathan Kirk when he proposed the idea of bring your own land. So rather than dropping your own files to disk, you download your tools from memory and run them from memory. he collaborated with Raphael Mudge, the creator of Cobalt Strike, to add that execute assembly command to the framework, which many red teamers are using as a commercial option. The reason they did this was because PowerShell had just kind of died violently. Microsoft added AMSI, which takes any script that's run through PowerShell and can pass it into your antivirus. So it gets the same treatment as if the script were being run from disk. And script block logging, which takes any script that's executed and just writes it to disk so you can actually look at everything that's being executed in detail. Because of that, most red teams that were relying on PowerShell started to transition away, and it was just easiest to do it to C#. So now let's go through some examples of this. Squibbly 2. So this is was a way to execute remote code on a server using a built-in Windows utility that's signed by Microsoft. So Wimic is a system administration tool created by Microsoft. You could pass it a URL with an XSL file, which is an XML file containing .NET code inside of it. So you're not even running an exe or a DLL, you're running a XML file. And these actually show up in a lot of different places. Theoretically, the XSL files are for transforming formats of XML that's being sent out. Another example of this is MS Build. It's another application whitelisting bypass. It's a signed Microsoft executable that's used behind the scenes for all compilation on your machine. So if you're building something like C or C++ or C#, it's using MS Build behind the scenes. Visual Studio uses it. You can give it an XML file that's properly structured with scripting code in it, and it will just run it through MS Build. And that way, if you can't run code anywhere else, you can run your Mimikatz or your whatever you want to from, again, an XML file. And it's an application whitelisting bypass. That was what we talked about earlier with, it's a UAC bypass using COM. I'm going to skip through that. Sharpshooter is a payload generation framework that lets you create payloads in all of those different scripting formats. So it can generate JavaScript, VBScript, HTA, which is a big thing right now. It can either let you load a .NET assembly or shellcode from memory, and the payload is encrypted for signature evasion. And it gets signatured every now and then people update it and it works for a while, and it gets killed and they update it and works for a while, so it might not work right now. An example of this stuff being used in the real world, if you heard recently about the Australian Parliament hack, all of their tooling, or almost all of their tooling, was written in .NET through C#. So this is an actual threat actor using it out in the wild. They used customized versions of Mimikatz functionality rewritten in C#, and they also used it for creating their RAT, their command and control, and doing a lot of their other tooling. However, SpectreOps was the group who really got all this stuff out into the public eye. So they released a whole bunch of public open source tools written in C# that red teams could immediately take and use in their operations. Most of them are for credential access and dumping, but Seatbelt is one of those that does system enumeration, shows you what AV is running and stuff. And then Sharpsploit is also written by a SpectreOps guy, and it's, rather than a bunch of pre-built tools, it's offensive libraries that you can use in your offensive tools that you create. So now let's actually see some malware. So this is Covenant, again created by the guy who made Sharpsploit. It is a whole RAT and command and control framework built off of the .NET framework. It has a client, a server, and the implant. So it's multi-user, which means you can have multiple operators connected to multiple servers. And if you've used PowerShell Empire, it looks pretty similar because it's the same guy who wrote it. It has a lot of the same functionality that every RAT does, but also has something interesting, which is the inline C# execution. So you can write C# like PowerShell, just write out lines of code, and it will dynamically compile it and execute it from memory. So that's what it looks like. All he did was write one line of C# code, like he was writing PowerShell, and it went and ran it. So you don't actually have to have an exe or a DLL or anything. You just write in C# at this point. And you have access to all of those offensive libraries at the same time. So now we're going to go through demos. So this is an example of a spearfishing payload that was published by Dominic Schell from MDSec Security. It lets you embed some VBA into an Office document that will load a remote XSL file from any URL on any event that you choose. So when he wrote it, it was pretty signature on VirusTotal. All I did was rewrite it a bit, so it got a 0. I don't know what it's got right now. But it uses a COM object to run the XSL file. And that's what it looks like. So that's an XSL file. It's a bunch of XML, but with some JavaScript embedded inside of it. And again, because it's not just JavaScript like would run in most browsers, it's JavaScript with access to all of the .NET framework and libraries. Let's see if it runs. So opening up the Office document, on the right is where the web server is hosting the XML file, and there you go, popped calculator. You can see it's actually running underneath SVC host rather than under Excel. So now we're going to talk about Silent Trinity. If you were in the previous talk, we're going to go over this again. It's a remote access tool that lets you bring entire languages into memory without them being present on disk. So through C#, you can load scripting languages that are not installed and run Python, Boo, and other languages all from memory without touching disk. So you use C# to get initial access, or use whatever you want to get initial access, and past that access, all of your post-exploitation can be written in Python on top of C#. So because Iron Python is a .NET implementation of Python, which is a really strange thing, but it's out there. And Boo is another scripting language. Both of them, all of their DLLs required to use a language are .NET assemblies. And logically, since you can load .NET assemblies from memory, therefore you can load those languages from memory. So Silent Trinity actually, within C#, embeds IronPython from memory. From IronPython, loads IronPython again from memory, and that second version is what you use to execute all of your modules and your tools. I'm not going to go through all the detail. So this, if you were in the previous talk, is what I showed as well. It's a way to load .NET assemblies from C++. So you can actually specify on a per file and per function basis whether your C++ code is compiled into machine code and runs directly on the hardware, or whether it's compiled to managed code, to CIL. So because you can't use DLL main in C#, so you can't have your code run whenever it's loaded into a process for DLL hijacking, you want something else that can. So C++ can do that for you. So all you do is you write some C++ that calls .NET version of C++, which, because it's .NET, can load assemblies from memory. And that's what all the C++ looks like. It's just normal C++ there, and the launch DLL right there is now a managed function. And it's hideous because I hate the syntax. Whoever designed this needs to go home and rethink their life because this is terrible. But hey, it works. And this is what it looks like. So all it's doing is loading the DLL. And when the DLL is loaded, it takes that .NET assembly from memory and stages a malware implant on the host. And now just to confirm that this actually worked, we're going to see we're even running in the process that loaded the DLL. So rather than our own process or run DLL32, we're actually running in that process directly. And we're going to run something on it to make sure, to prove that we actually have access. Come on. There we go. And that was written in IronPython, I believe. So you're running Python through C# through C++. I'm going to skip that one. So these slides were made for an hour-and-a-half talk, and I'm just kind of skipping through stuff because I have way more content than I need. So this is interesting. There are a number of well-known ways to bypass AMSI, which is the anti-malware system for PowerShell. So all you have to do is from PowerShell, load a C# program from memory that does one of those bypasses, and then even though so if you just write it in PowerShell, AMSI gets the script that bypasses PowerShell or bypasses AMSI before it executes. So it can look for stuff that disables itself. But if you write it in C# and load it from PowerShell, then it completely bypasses that. We're going to see this real quickly. So what I'm doing here is ran a command that's known to be malicious, and it says you cannot run this because it contains malware. So now we're going to do a bunch of really nasty stuff, paste that in, bunch of base64, and the console can't keep up because there's so much stuff. There we go. And we run it. So it's okay, we bypassed AMSI, and now we rerun the same malicious script up above, and boom, no alert. So .NET to X, this is just a demo of the MS Build application whitelisting bypass that I showed earlier. We're going to use MS Build, a legitimate signed Microsoft binary, to load .NET code from memory through an XML file. And again, this is all it looks like, just XML with a whole bunch of C# embedded into it. And this is raw C#. It's not even a compiled .NET executable. You just throw C# into the XML and it runs it. And here we go. Just to show you, it is C#. Contains code to unpack the payload, load it from memory. And now we're going to go back over there, run MS Build with the XML file. And hello world. There you go. Ran the C#. I had to make it complicated by loading C# inside C# just because. So this is another tool that will generate. So you know how I said you can't inject .NET programs into processes? Well, you can as long as you have native code that doesn't have to be interpreted that can bootstrap your .NET code. So you inject native code, which loads the runtime environment, and then loads your managed code from memory. So this is a framework that me and another guy worked on that can take an arbitrary assembly, generate shellcode for it, and you can inject now your .NET assembly into any process. So the procedure is, if the runtime environment is not already present, load it, create an application domain, go get your .NET assembly from memory or from a URL, decrypt it, put it in the application domain, wipe the decrypted assembly from memory to deter scanners, then run your assembly with parameters. And this is messy. So let me explain about what's going on. At the top, again, this is Silent Trinity. So at the top, I ran a tool to show all processes running on the machine to choose what to inject into. Then I ran a .NET assembly from memory that injected my shellcode into a process that I wanted it to run out of. Again, got a callback from it. Now I use the built-in shellcode injector, inject it into whatever process I want. Again, get a callback from it. This is just to prove it does work. You can actually inject .NET now into any process you want. And just to prove this, Chrome, we're running inside of Chrome. Chrome would never, ever load .NET code, but now you have your Silent Trinity rat running outside of Chrome, running inside of Chrome. This does produce anomalous behavior, though, because if you, the managed column says whether or not the process has the common language runtime loaded at all. Only one of them does, right? So it's a process that normally would never use .NET, which now has the .NET runtime loaded. That's pretty suspicious. So what about detecting all this stuff? So there is AMSI. There's also event tracing for Windows. If you want to Google things, those are the things to Google. Event tracing for Windows and AMSI. As far as behavioral monitoring, you can also look for odd loading of DLLs and modules. Like, for example, if they're loading the .NET runtime and they're not a .NET process, it's probably .NET injection. And signatures, but signatures are not really reliable. So in the new version of .NET that just came out, even .NET assemblies that are loaded from memory will now be sent to AMSI. So they finally fixed that giant loophole of being able to load any code you want from memory, but you can bypass it. So all right, so when you install .NET 4.8, it puts AMSI into .NET 4.0 and higher. So any code that's run that was compiled for .NET 4.0 or greater will now be passed to AMSI and scanned by antivirus, if it uses AMSI. So all you have to do is compile it for 3.5, right? 3.5 doesn't have AMSI, so it doesn't use AMSI. You can also, if you actually need to use .NET 4.8 code, you just load it from memory using 3.5, and again, it doesn't have AMSI. So the downside of that is that 3.5 has to actually be installed on the system, and it's not by default on Windows. It is on older versions of Windows. And I said other bypass. When I wrote this, I said other bypasses will probably be found soon, but for Dotnet, we actually created several bypasses, so that's not a probably. So event tracing for Windows. There's a tool out there called Silk ETW. That is what you want to Google. That is the one you want to write down. He also created a service version of it, which can run as a service on Microsoft, on Windows. It uses event tracing for Windows to monitor anything that event tracing has access to. One of the things it has access to is pulling out every tiny event associated with the .NET runtime, including loading things from memory, including every function that executes. And you can also match that at runtime to Yara rules. So if you have a Yara rule for whatever malware you're trying to detect, get all that information, filter it out, throw it through a Yara rule, get the detection, and you can even send the result as JSON to a URL, so you could have it go to your elk stack. So if you want to be detecting this sort of stuff, that's what you look at right now. It's the only thing out there right now that has any hope of detecting this stuff. And this is the other way. So when we released Dotnet, we also released this description of anomalous behavior that shows you how to detect it through DLL loading. So all of the .NET runtime DLLs start with MSC, have some other stuff, and then are .dll. The only DLLs I know of in existence that have that expression, that format, are DLLs associated with the Microsoft runtime, or the .NET runtime. So all you have to do is say, anytime a process loads this DLL, check, is that process a .NET program? If not, .NET has been injected into it. And that's what it looks like. So I wrote a very, very basic tool that uses WMI events to look for this. And it shows the test load stuff that I was using to stage Silent Trinity and use for COM, it detected that. It detected, say, hey, .NET code has been injected into a process. You could try signatures, but they're probably not going to work. The one that might work is that Cobalt Strike's execute assembly has a very, very predictable way that it executes. It uses whatever was configured for the spawn2 command in Cobalt Strike. It does, whether that's by default, it's run DLL32.exe. It will create a process with that executable, use reflective DLL injection to inject unmanaged code into it that loads your .NET assembly and runs it. If you can build an analytic for that behavior, then you can generally detect execute assembly. But that's a signature of that particular tool, right? So it won't work for other tools that do similar things. So what next? I mean, I think when I submitted these slides, it didn't have the AMSI stuff on it. So .NET 4.8 with AMSI is the biggest deterrence getting in the way of .NET exploitation in the near future. It's not perfect. It can be bypassed, but it will still deter most people. It can be bypassed in the same way that PowerShell can be bypassed. So the stuff that I showed earlier where we bypassed AMZ and PowerShell, pretty much the same thing. And there's a lot of different ways you can do it. But remember, scanning is not equal to detection. So just because you can scan code that's being loaded doesn't mean you actually detect it as malicious. So you still have to get that part figured out. Again, I wrote this before the AMZ research. I don't believe it will be the downfall of .NET Tradecraft like a lot of people did, because again, it can be bypassed. The other neat thing coming up, or neat for Red Team, is offensive DLR. So all of the Iron Python stuff, there's the common language runtime. And then Microsoft went and made the dynamic language runtime, which runs on top of .NET and lets you write any scripting language you want. Well, that's what he's abusing, because the .NET language runtime is built for loading, generating, compiling, and executing code from memory. That's what it's built from the ground up to do. And it's a Microsoft tool. It's a feature. They provide it as, they support it. They heavily support it. So it's not going away anytime soon. Bytebleeder, who made Silent Trinity, he's the main one looking into research on this stuff, but other people are as well. You don't even get, so the AMZ stuff only works for that one function that loads assemblies from memory. It doesn't work for any of this DLR stuff instead. I should note that AMZ works regardless of how you load the assembly. Just going back here real quickly. So this works against execute assembly. It works against Donut's shellcode. It works against everything that loads assemblies from memory. It can be bypassed, but it's still, when it works, it works. And that's all I had. So questions?